purpose of this video is to show you how to use Kirchhoff's rules to analyze a circuit. So the first thing we have to realize is when we talk about circuit analysis for this circuit, the only thing that we don't really know is current. The other thing that we should be able to identify is that there's really only three currents that we have to worry about. So the three currents we have in the circuit is the current leaves the battery and goes through this first resistor, and we have current then that goes this way at junction B, and then we also have current that goes this way. They continue back to junction E, and we have both of these currents coming together to form the same current that we had up here. So the first step in using Kirchhoff's rules is to label the currents in a way that's useful and meaningful. And the only place we really need to know a particular current is when it's going through a resistor. So what I'm going to do is I'm going to label the current here as IT for total current. I'm also going to label the current here as IT also because it's total current going through that branch as well. Next, just to help me remember, I'm going to label the current going through the 3 ohm resistor as I3, and I'm going to label the current going the other branch as I2 because I go through the first resistor, which is a 2 ohm resistor. This will help me kind of remember and keep track which current goes where. It's also important to note that the current through the 6 ohm resistor and the 4 ohm resistor are actually the same thing as current 2 because they're in series. At this point, we've established the three variables that we don't know in this circuit. So the rest of the circuit analysis becomes a question of how can we come up with the equations to help us solve for those three currents. You learn in math, if you have three unknowns, all you need is three equations that relate to each other, and you can solve for all three of them. So that's what we're going to do using Kirchhoff's rules. The easiest equation to get is the equation using Kirchhoff's junction rule. If we look at junction B, it's easy to say there are three currents that are involved with that junction. We have one current going in and two going out. So the equation is really easy. The total current is equal to current 3 plus current 2. Now it's worth mentioning that we could use the junction rule at junction E, but the problem is we're going to end up with the same equation, right? Current 2 plus current 3 is going to be equal to total current, which we already know. So for our other two equations, we have to use something different. This is where we'll look to the loop rule. The idea with Kirchhoff's loop rule is that if we start at some point in a circuit, we go all the way through the circuit, all the way back to the same point again, our change in potential will be equal to 0. So we can use this idea, sum all the voltages in that current, and they should all add up to 0. That will help us develop a new equation. Watch. If I start at point F, the first element I come to is the battery, or the voltage power supply. It's 24 volts. So if I go from F to A, I've had an increase in voltage of 24 volts. I can make that the first thing I sum into my equation, 24 volts. The next element I come to is the resistor 1. Now, this is going to cause a drop in voltage because there's current going through it. And if we're going through the circuit in the same direction as the current when we're analyzing the circuit, then, like I've said before, it's sort of like a waterfall. We have a drop in voltage because we're going with the current through a resistor. It's a drop in potential. So the next voltage that I account for is the voltage across R1. The problem is I don't know what it is. The only thing I know is the resistance there, but I do know my unknown total current is something that I'm looking for. So I can add this in terms of the Ohm's law. I could say 5 ohms times IT. And we sum this in as negative because it's a drop in voltage. And we're on our way to developing a second equation. So at this point, the next element I come to is R3. And again, I'm going with the current through a resistor, so I can do the same thing I did with the first resistor. The the voltage across resistor 3 is 3 ohms times I3. And again, this is a drop in voltage, so it's negative. Doing this one more time, we would get our last voltage drop across R6, 4.75 ohms plus IT. Now we can simplify this equation. At this point, I also notice I drop all the units because whatever number we end up solving for is going to be in amps since we're solving for currents. The next thing we can do is use the loop rule again to find the change in voltage in a different loop to get our third equation. This time starting at point E, going through resistor 3, and from point B to C to D to E. So in this case, my first element is R3 again, but I'm going up through it. So I list this voltage as positive. My next element will be R2, and this time I'm going with the current through resistor, so it's going to be a negative value for my voltage, and it will be 2 times I2 by resistance times the current. The next element is R4, going with the current. It's a drop in voltage, so this time I get 1 ohm times I2. Finally, the last element I go through is resistor 5, which gives me a drop in voltage because I'm going with the current through resistor 5, so I get 6 times I2. That gives us our third equation, and all we really have to do is simplify it a bit. It does simplify pretty easily into 9 times I2 is equal to 3 times I3. We can simplify it one more time. So finally we have 3 equations and 3 unknowns, and this will allow us to solve for all of our unknowns, all of our currents. The easiest way I've found to solve for these is to substitute the other 2 equations into this one. So if I take this equation and solve it for I total, I can substitute it into the equation in terms of I3. I can also substitute this equation in terms of I2. Then I can also substitute that in the junction equation in terms of I3. So I total, which is 24 minus I3 divided by 9.75, equals I3 plus I2, which is 1/3 I3. Now I can solve for the I3 at this point. You can pause it here and look at the algebra if you want. But here we can show that I3 is equal to 1.5 amps, which is what we got before. Now we can use that and plug that back into our original equations. This one tells us that I2 is going to be equal to 1/3 I3. That means I2 is equal to 0.5 amps. And at this point, it's actually easier to go back to this equation and say that I total is equal to 2.0 amps, just the sum of these two. I believe you find that these are the same answers as we got at the previous analysis of the same circuit, but this is Kirchhoff's loop rules. Good luck.